Okay, so before we get started into the calculus of our notes, I do want to take some time to talk about the inverse functions, the inverse trig functions, and what they look like. Okay, you talked about this briefly in pre-calculus last year, probably briefly enough to where you might not remember what they actually look like. You worked with the inverse trig functions quite a bit, but not necessarily their graphs. Okay. So we just talked about inverses. Does this graph pass the horizontal line test? No. No, this horizontal line test, or the horizontal line is going to go through it an infinite number of times. Okay. So this graph would not have an inverse. If we took the inverse, it would look like this. Okay, that function. So what happens is if we only take the part of y equals sine of x from negative pi over 2 to pi over 2, then does it pass the horizontal line test? Yes. So then when we take its inverse, we have what looks like this. Okay, we have enough of it to where we get all of the values around the unit circle, but none that repeat, so that we still are 1 to 1. Okay, so what happens is for our inverse sine, remember, sometimes we call it arc sine. Remember that notation? Okay, its domain is negative 1 to 1, and its range is negative pi over 2 to pi over 2. Once again, our cosine graph would not pass the horizontal line test. Do you see how if we kept this going, horizontal line would go through it more than once? So if we restrict it to what I have here in red, okay, we get each value from the unit circle and none that repeat. So we have like a nice little unique squiggle is kind of what it looks like. Okay. But it passes the horizontal line test, and so when we take the inverse, we actually have a function. Okay, we notate it y equals arc cosine of x, or you'll see the cosine inverse of x. Both notations I need you to be familiar with. But here again, our domain is negative 1 to 1, but inverse cosine is different. Its range is 0 to pi. Okay. The reason for that is, if you remember back to our unit circle, like for sine, quadrants 1 and 2 are both positive, all right? And so, but for cosine, quadrants 1 and 2, cosine's positive in the first, negative in the second. So if we stick to the first and second quadrant, 0 to pi, we have all of the positive, all of the negative values from our triangles, okay? And then our tangent function. Okay, our tangent function, remember, we have this repeated over and over and over and over and over and over again. But if we just take one sliver of it, specifically from negative pi over 2 to pi over 2, then it passes the horizontal line test, and this is your arctangent graph. Okay, the domain of this guy is all real numbers, and its range is negative pi over 2 to pi over 2, just similarly to sine, inverse sine, but we have asymptotes, so we can't include those endpoints. Okay, this is a graph that will pop up more than you think. So I want you to really just think through this process with me. I know that you're at least more familiar with y equals tangent of x because you graphed those last year. When we think about reflecting that about the y equals x line, we get a horizontal tangent of x, okay, for our inverse tangent with those two asymptotes. Okay. All right. On the back side of your notes, I do have written out the domain and range of each of those. I don't know if it's like 100% vital that you know these. But just for some of the understanding of where things come from, I want you to be aware that this is the case for our 6 inverse functions. Okay? Now, what I'm going to do is I'm going to show you where one of the derivative rules comes from. This is not something I'm going to ask you to ever reproduce, but I want you to kind of get an idea of where things are coming from, and then we'll write down the rules there in the middle of that page. Okay? So just go along with me. Okay? I want to know what the derivative of inverse tangent is. Okay, and we have a rule for it, and by the end of today, I want you to walk out of here knowing that rule. You're going to have to spend a couple days probably working with it to really remember it, but I will repeat, what I am doing on this slide is not something I would ever ask you to reproduce, okay? Like in a test quiz situation, okay? I just want to know where is it coming from. So, if y equals inverse tangent of x, okay, that really just means x equals the tangent of y. All I did is I rewrote it so it wasn't an inverse anymore. Okay? And if x equals the tangent of y, we could draw a little picture here. Our angle is y, and our tangent ratio is x. So like opposite over adjacent needs to equal x. So opposite over adjacent, x over 1. We could write that ratio. All right. Now, what I'm going to do is I am going to take the derivative of x equals tangent of y. We can do that, right? We know how to do that. What's the derivative of x? 1. The derivative of tangent of y? Secant squared y dy dx. Okay. So, dy dx is 1 divided by secant squared y. Is there a prettier way to write 1 over secant squared y? Say it louder. Say it louder. Cosine squared y is the same thing as 1 over secant squared y. Okay? All right, well, that's not really helpful because it has a y in it. Okay? So what I'm going to do is I'm going to come back to this triangle right here. This right triangle right here. And using the Pythagorean theorem, leg squared plus leg squared equals hypotenuse squared. Our hypotenuse would be the square root of x squared plus 1. Okay? Just use the Pythagorean theorem to get that. Okay? Cosine squared y. We determine the cosine by taking adjacent over hypotenuse. Is that right?
Yes.
Okay. So what's our adjacent side for y? Our adjacent side is 1. Our hypotenuse is this right here. So what I'm going to do is I'm going to rewrite this as cosine squared, but our cosine of y is adjacent over hypotenuse. Which is 1 over x squared plus 1. You see that box where it has all the rules? Find the derivative of arctangent. It's like the second one in the left column. Write 1 over x squared plus 1. Okay. Am I ever going to make you replicate that? No, I am not. What I want you to be able to know is that the derivative of inverse tangent is 1 over x squared plus 1. And here are all of the rules. I would like you to write them down. And I will tell you which ones you need to memorize and which ones you don't.
Sure.
Let's see. I realize these derivatives are kind of crazy, and it's a lot to take in. On a test situation, I would only ever ask you arc sine, arc tangent, or arc cosine. Okay? So in your homework today, if you have an arc cotangent, arc cosecant, or arc secant derivative, it is fine for you to look at your paper, and you're probably going to use this paper to do your homework, and I get that. But come time for your test, you need to be able to remember those 3 that I put a red star on. Now the good news is that arc sine and arc cosine have a very similar derivative. One is just negative. Okay, and it goes with the cosine, which is kind of nice because the derivative of cosine is negative. All right. And then the arc tangent, it's different, but they're not. So we're going to go through the 4 examples that you have at the bottom of your sheet. Okay, and when we're done with those, we're done with those. All right. So, first example. The derivative of y equals arc tangent of 2x. Okay, what you need to keep in mind is that this rule that you have written down is for arctangent of x. Okay, well now we need to apply it to arctangent of 2x. Okay, we're going to do that just like we would any other derivative. What is inside stays inside, and then we apply the chain rule. So when we talk about this derivative, okay, we're going to talk about using that rule of 1 over 1 plus x squared, but what's inside has to stay inside. So instead of x squared, inside of arctangent is 2x. So that has to stay inside of our rule. All right? But then we also have to use the chain rule. The derivative of 2x is 2. So our derivative would really be 2 over 1 plus 4x squared. Just like any other derivative, what's inside stays inside, and then you apply the chain rule. Okay. Look at the second one. Okay, I'm just trying to write the rule so we can reference it visually up here. Okay. All right, so here's our rule for arcsine of x. We have arcsine of radical x. Okay, so just like any other derivative, we're going to use the rule, keeping what's inside, inside. So our rule is 1 over radical 1 minus x squared. So inside of our arc sign is radical x. So that's where that's going to go. But now we have to apply the chain rule, right? Now we have to take the derivative of the inside, which is radical x. Remember, x is the 1/2 power. So the derivative of the inside would be that. Right? And to be honest, I am perfectly happy with you just leaving it like that. Okay? You want to rewrite it, that's fine. But to avoid an algebraic mistake and just focus on the derivative, we can just leave it like that. All right, so how about you try example 3 at your pod? Example 3 is arcsecant, which, yes, I realize is not one you have to memorize, but I'd still like you to be able to apply the rule. So at your table, work together to take the derivative of the arcsecant of 7x squared plus 1.
All of it from one hand. One hand times the inside. You just look at it as x. Yeah.
No, just 3. Just 3. That was adorable.
I got it.
All right. Does yours look like mine? Okay. Since your rule was arcsecant of x, wherever there was an x, you had to replace with that inside, 7x squared plus 1. And then applying the chain rule, we need to multiply by 14x. All right, we have done 3 examples that have just been use the rule, right? Okay, so let's stretch our brains a little bit and do an example where it's not just the rule. What do we have going on in example 4? We have a product, which means we should use the product rule. Okay? So, the derivative of our first function. Andre, what's the derivative of our first function? 2x times the arc cosine of x plus our first function times the derivative of our second. Eli, help me out with that one.
-1 over the square root of 1 minus x squared.
Good. You want to rewrite that, feel free, as like a subtraction with x squared in your denominator, or you can leave it like that. That's fine too. Okay. Biggest challenge is just going to be remembering these rules. Okay? They're kind of the craziest. Okay? But guess what? You have an entire week. You got it. All right, so we have like 8 minutes left in class. Find either a picture of the book page or a book to share at your table. And I want you to at least get 2 to 3 of your homework problems done before you leave. Okay? Yes. Let me stop the recording real quick.